Hello, and welcome to lesson 29 of this introduction to calculus with Wolfram U. The topic for this lesson is volumes of solids. So let's begin with a brief overview of today's lesson. Thus far we've been talking about the area under curves, and we've used integral calculus for doing that. So for example, if you work out this integral over here, then what you're really doing is to work out the area under the curve y equal to x squared between 2 and 3. But the point is that you can also use integral calculus to find the volume of solids. And that would be a big advance if we could learn it. So let's look at a very simple example of a solid, like over here. And what we can do is we can actually calculate the volume of this solid or others using calculus. So this lesson is about one method for computing such volumes. So the solid that we spoke about just now was a cylinder, of course. And if you think of a cylinder, it can be constructed by taking a plane region and then you sweep out a volume. So for example, let's say you take this disk over here and you sweep out a volume up to a certain height and you get a cylinder. Now that's a hint for finding the volume of a cylinder, namely you think of it as being composed of disks. So if you want to find the volume of a cylinder, what you do is you take the base area and then multiply it by the height to get the volume. So for example, here's a disk. You can work out its area, and that's a cylinder with that disk as a base and height 4, and its volume is 4 pi. So basically the volume of a cylinder is the area of the base times the height, which is 4 in this case. Now, of course, there are many more shapes and solids in the Wolfram language, and you can work out their volumes directly, but what you might want to do is to work out the volumes of even more general solids. So here's an example. You have a three-dimensional region, and if you look at this region, you think of it as being composed of square cross sections. So if you were to slice the region, you would see that the area of each piece is 4x squared because you have squares with lengths and widths of 2x. So the volume of each piece would be 4x squared times delta x, and then you can add them all up, so to speak, and get the total volume to be the integral of 4x squared dx between the right limits. So for example, if you want to find limits as 1 and 3, then the volume is 104 over 3. Okay, so now let's try and generalize that a bit more. So if you have a solid with cross-section area A of x, then its volume is the integral from A to B of A of x dx, where A and B are the limits within which you want to find the volume. So for example, if you want to find the volume of a ball, like over here, and the radius is r, then each cross-section has got a radius of square root of r squared minus x squared. So the cross-sections at the left end have got very small area, and as you go to the middle, the area increases. So basically, the area will be pi times r squared minus x squared. You add them all up, and you get the volume of the ball, which is, of course, 4 pi r cubed over 3. And you can check that with volume and get back just the same result. Okay, so let's use the same idea to talk about what are called solids of revolution. So here's a function, and what you can do is you can take the graph of this function and revolve it around the x-axis, and then you get a solid. So here's how you do it. Use revolution plot 3D, and you get this solid obtained by revolving the curve about the x-axis. Of course, you could also revolve on the y-axis and get a slightly different solid. So the question is, how do you work out the volumes in these cases? Okay, so what you do is you can again divide the volume into disks, but in this case, each cross-section is a disk whose radius is f of x, the value of the function f at x. So the volume will be the integral from a to b of pi times f of x squared dx. So let's say you want to find the volume from -1 to 1. So you get back the integral over here, which is 2 pi over 5. So just to remind you, that was the original parabola, and that was the solid obtained by revolving around the x-axis. Now, you might, let's say, want to revolve it around the line y equal to 1, in which case you just subtract off 1, because if you look at the volume over here, you see that you actually have different radii depending upon where you are. So basically shift down the function by 1 to get the correct picture. And then the radius of each cross-section is 1 minus f of x, so you can work out the volume as the integral of pi times 1 f of x the whole square between the correct limits. Similarly, if you want to find, let's say, the volume obtained and revolve around the line y equal to -1, then you add a 1. So here's the picture. Again, work out the volume with an integral, and you get back the answer. So basically shift the function up by 1 in this case. Now, a second method for computing volumes is the so-called washer method. The idea is this: suppose you have two functions f and g, and you look at the area between them, and then you revolve it around the x-axis. So here's a nice demonstration of that. So you revolve it, it sweeps out a volume, and the question is, how do you work out a formula for that volume? So what you do is, you remind yourself that now each cross-section is like a washer, because it's got a kind of outer and inner radius. So that's the area of this washer. You work out the integral for the volume, and that's the method for finding the volume using the washer method. But of course, you might have liked to go around the y-axis, in which case you do just the opposite. You write f and g as functions of y, and then do a similar integral to get back the answer. So that brings me to the end of the lesson. So the main point is that you can use integrals to find the volumes of solids, and that's quite a powerful idea. So let's say if you have a cylinder, then its volume is base times height, where capital B is the area of the base. And if you have a more general solid with a cross-sectional area A of x, then you can compute an integral to find the volume. If you have a solid of revolution obtained by revolving a function around a certain line, then you can compute its volume using the formula over here. Now, typically, you might just want y to be 0, so you're revolving around the x-axis. But if you have two functions and you want to revolve the area between them, then you apply the washer method and apply the formula over here. And of course, you can repeat the same thing for revolving around the line x equal to x naught. So that's the end of this lesson about the volume of solids using the so-called disk method and the washer methods. And in the next lesson, we'll talk about another method which is called the cylindrical shell method. That's a little easy in some cases, but that's for next time. So do review today's lesson. It's quite a difficult lesson, and I'll see you next time. Thank you very much. I'll stop over here.